Hey guys, how's it going? In this video we're going to go over question 2 from the 2015 Exemplar SQA Advanced Higher Physics exam paper. So let's get started. Question 2 says a motorised model plane is attached to a light string anchored to a ceiling. The plane follows a circular path of radius 0.35 metres as shown in figure 2. So there's the circular path shown there with the radius of 0.35 metres, and then you'll see we've got this angle theta that's being swept out by the model plane. It then says the plane has a mass of 0.20 kilograms and moves with a constant angular velocity of 6.0 radians per second. Part A says calculate the central force acting on the plane, and you'll see it's worth 3 marks. Well, remember central force is just another phrase for centripetal force, so we just need to calculate centripetal force here using one of the equations from the relationship sheet. So writing down, we know from the question we're trying to find centripetal force F, we know the mass of the plane is 0.20 kilograms, we know the radius of the circular path is 0.35 metres, and the angular velocity omega is 6.0 radians per second. So we're going to use the equation that relates centripetal force to angular velocity instead of the one for centripetal force in terms of linear velocity. So writing down the correct equation from the relationship sheet, we have F equals mr omega squared. Substituting in the numbers gives us 0.20 times 0.35 times 6.0 squared, and putting that into your calculator should give you an answer of 2.5 newtons. Part B says calculate the angle theta of the string to the vertical. So if we look back at the picture, we want to calculate this angle theta, which is the angle of the string to the vertical. And to do this, we need to think about the forces acting on the plane. So in order for the plane to keep moving in circular motion, there must be a centripetal force acting on the plane, and we've actually just calculated that in part A. And this centripetal force would be acting in towards the centre of the circle at all times. So that would be a vector going horizontally in towards the centre here. And because the plane has a mass, that means it must also have a weight acting downwards on it. So let's start by drawing a free body diagram to show those two forces acting on the plane. So let's just draw my mass, my plane, as a circle, and then we can draw the force going downwards, which is our weight, or we can call that mg instead because W equals mg for weight. And then assuming the plane is over at the right hand side of its motion, just like in the picture, that means we could draw the centripetal force acting to the left and call that F. Now what we can say is that since the vertical forces acting on the plane are balanced, we can redraw this as having the mass or the plane at the bottom. We could then have our weight or mg force going up the way, and that's because we're saying the vertical forces are balanced here. So because we've got mg acting downwards, that would be the same as mg acting upwards. And we can keep the centripetal force going to the left just like before and label that F again. Now the reason we've done this will become apparent in a minute when we see what the final vector diagram looks like. Now we want to determine a resultant force here, and you'll notice that we have two vectors that are not joined nose to tail. So what we want to do is add the vectors nose to tail. So if we draw the mass here and then the centripetal force F going to the left again, what we can do is take that vertical force mg and move it so that the tail of that vertical force joins onto the nose of this horizontal one. So it would look like this when you've moved it over. And you'll see there we've got nose joining to tail, nose to tail. So that means we could draw the resultant vector going from the start to the finish point, and we'll put a double arrow on that to show it's a resultant vector to make it different from the single vectors. And let's label that as the string, but it would actually represent the tension force in the string as well. But we don't really need the tension force for our analysis here. Now let's put in a right angle there to show it's a right angle triangle, and you'll notice this triangle looks very similar to the shape of the triangle we've got in the diagram in the question. So here we've got our mass, we've got our string, which is our resultant vector, we've then got our vertical and our horizontal. So if we were to make this into a triangle, it would look just like our right angle triangle that we've drawn. And that means we can label this angle in here as our angle theta on our diagram. So let's label that angle up there as theta, and remember that's what we're trying to calculate. So because we've got a right angle triangle and we know two sides and we're trying to find this angle theta in here, then we can use trigonometry, i.e. SQA, in order to find out what this angle theta is. So for my angle theta, you'll notice I've got the opposite side. I know that's the centripetal force F, and I know what the adjacent side is, mg. So if we use SQA and I know the opposite and adjacent sides, then that means we're going to use tan. So we can start by saying tan theta equals opposite over adjacent, which is equal to the centripetal force F divided by mg for the weight. And that's equal to 2.5 newtons, which was our answer to part A, divided by 0.2 for the mass times 9.8 for the gravitational field strength on Earth. And if you put that into your calculator, you should get an answer of 1.28. However, remember we want theta, not tan theta. So to find theta, we can do the inverse of tan of both sides, or shift tan in your calculator. So the inverse tan of 1.28 should give you an answer of 52 degrees. Lastly, part C says state the effect a decrease in the plane's speed would have on angle theta. Justify your answer, and you'll see it's worth 2 marks. Well, in this question, we were talking about angular velocity of the plane, and you could answer this by thinking about angular velocity or linear velocity, but because it just says plane speed and not the plane's angular speed here, then let's just assume they mean linear speed or linear velocity v. So what we could say first of all is that if the plane's linear speed v goes down, i.e. decreases, then so does its angular speed omega, and that's because these two variables are directly proportional through the equation v equals r omega. So if v decreases, then omega must decrease as well. Now we can say that if the angular speed decreases, then so does the centripetal force. And that's because centripetal force and angular velocity are also directly proportional from the equation that we used in part A, F equals mr omega squared. So just to show you that one again, you can see that F and omega squared are directly proportional, and therefore F and omega would be directly proportional as well. Now if we look at our equation up here that we used to calculate tan theta, you can see that centripetal force F is on the numerator of this fraction. And that means that tan theta and centripetal force F are also directly proportional. So if the centripetal force decreases, then that means that tan theta must also decrease. And by default, tan theta and theta are also directly proportional. So if tan theta goes down, then theta must also go down as well. So we can say therefore the angle theta decreases, and therefore we can conclude that angle theta would decrease as long as weight stays the same. In other words, as long as this weight, the denominator in the fraction mg, stays the same. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.